Wanna take control of your memory? Time to write a custom allocator. So what are allocators? Allocators are objects responsible for encapsulating memory management. They are used all over the standard library, in particular the STL. Standard containers use them to manage all the memory inside, and basically you don't have to worry about it. By default, the standard containers use a default allocator called simply standard allocator. So if you write, for example, a vector of ints, some vector, the second template argument, which is not shown here, is simply a standard allocator, and that is how you can provide your own. Okay, but why would you want to provide your own allocator since the default ones are doing their job just fine? Well, there's a variety of reasons. In particular, you might be interested in statistics, or maybe you have your own low-level memory management functions which outperform the default ones. Whatever the reason, you can do that. Let's see how. First, let's start with our basic vector. Let's initialize it with some 5 ints. Their value is not important. And let's build our allocator skeleton. Okay. Let's call it a tracking allocator, since we want to track the amount of allocations and the allocations done. Let's write our constructor and destructor and proceed from there. So we have our skeleton. Let's just pass that as a template argument. And now the vector will default construct an allocator of our type and use it to allocate memory. But how does it do that? Let's fill the details. The allocator itself needs some type defs of aliases in order to make it work. In reality, the only alias you need is one called value type. But what should be this value type? Well, we want our allocator to be generic, so let's make it a template to handle all kinds of objects. And in this case, our value type is just the type we pass in. So now we need to just adjust a bit. Okay, so now we have our basic allocator. Will it compile? No, because we need some more stuff inside. Before digging into the whole allocation and deallocation, let's stay a bit with the aliases. You see, this is the only required alias inside the allocator, but there are some optional which you can provide. Let's just list them so you will see what they are and how to use them. Small note: some implementations of the standard library may not be fully standards conforming, and they might need some aliases which aren't really needed now. But we'll assume our standard library is standards conforming and we'll just go with that. Let's start with 2 optional aliases called pointer. A pointer is just an alias for a pointer to our type, the pointer. We have a similar one called const pointer, which just is an alias for pointer to const. Okay. Why are these optional? Well, because there is a structure called allocator traits which provides such defaults if your allocator doesn't provide them itself. And the standard library uses the allocator traits to get all those aliases. But let's move on. Another alias is something called a generic pointer. This is a pointer to which all other pointers, including your one and basically any there are, should be implicitly converted. We have such thing in the C++ language, it's a void pointer. And guess what? The alias itself is called a void pointer. Right. And similarly, we need a constant version. Okay. We also can supply two optional aliases. One represents a size which will be used in our allocation and deallocation functions later. We will see. Of course, this is optional. Size t. And another alias represents a difference between two pointers. So, we have a bunch of aliases. We really need only this one. These are optional. You may not supply them at all if you like these defaults. So now let's move to the actual allocation and deallocation of objects. The allocation function, or method rather, it's called simply allocate. This method should return our pointer. So let's use our alias. That's where it comes handy. Allocate. As a parameter, it gets the count of objects it should construct, not the size of the memory. The count of objects. Size type, non-objects. Okay. And how should we allocate? Let's use the global operator new. Start pointer from operator. Oh, here it is. Let's call it size of t times num objects. And that's it. That's our required allocation function. The other method which is required in order for the allocator to work is the deallocation function, called deallocate. It takes a pointer, the previously allocated memory, and num objects parameter, which might be handy if you want to know how many objects you allocated before. Okay, so how should we do it? Let's call operator delete on p. Small note here. These are the two functions which are really required. Other are optional, like our aliases. But I have seen standard library implementations which require at least one more optional function. This one is called max size. It should return the maximum number of objects our allocator can allocate. So let's write one just in case. Let's use numeric limits and just return them. Numeric limits for size type max. And that's it. There are other optional methods. Let's just write them. There are defaults which simply work fine, but let's see what they are. There's another version of allocate, another overload, which also takes num objects parameter, but takes something called a locality hint. It's a pointer to the nearest element which was allocated previously. You can use that to improve the locality of your allocated memory just to improve cache performance. In our case, because of a pointer hint, in our case we'll just ignore it and return the allocate result, like that. Now we have two optional methods for constructing and destroying objects. One is called construct, and it's used to construct the actual object of our type in the memory which we have allocated. Note here that we are calling operator new, which allocates raw memory. It does not initialize, does not construct the objects anywhere. Let's see how the construction function works. A construction function should be a template. It should work on some type U. It will be probably the same type as T, but it's not necessary to. And it should take any number of arguments which are then passed down to the constructor of U. So let's use variadic templates. 3 args. Okay. Our method is called construct. It takes a pointer to U and the arguments. It should call in place new and just pass those arguments to the constructor. Okay, it's really simple. It constructs in place an object and forwards arguments. Now let's see about the similar optional method called destroy, which is used to destroy the object. It also should be a template for some class U, be called destroy, and it should take a pointer to U. This pointer is assumed to be previously allocated and constructed, so you can safely just call this destructor, and that's all. This is totally optional. By default it behaves just like that, and you don't need to write any of this. Now let's see if it all works. Nope, I made a typo somewhere. Where? Oh, here it is. On that. Okay, let's see now. Ooh, something has gone bad. Let's see what happened. Cannot convert some wrap allocator from our allocator to const our allocator reference. What is going on here? It means that something is using another allocator other than ours. So how come something is trying to use another type of allocator when we explicitly provided the type ourselves? You see, there is a mechanism called rebinding allocators. If you have an allocator of some type, but you don't know what type it is, you might be wanting to use that allocator to allocate another type. Right now we are using an allocator of int to create ints. But let's suppose our vector has some internal structures which it needs to allocate, and it wants to use our allocator to do that. But it cannot use a tracking allocator of int to create those structures. It needs a tracking allocator of some internal structure to use it. That's where the rebinding comes in. A rebind is a way to use an internal type def or alias of an allocator to create another allocator like this one, but working on different types. You have a default rebind mechanism in place in the standard library, so you really don't need to write your own. But let's see for completeness how does this mechanism work. let's suppose you have an internal template structure called Rebind. And in this structure, you have an alias called other, which is simply our tracking allocator of you. Now, by using this internal rebind, we can convert our tracking allocator of one type to a tracking allocator of another type. For example, we might have our using tracking allocator of int being tracking allocator of int, but if you wanted to use a tracking allocator of, let's say, double, you could write tracking allocator from double is a tracking allocator of int rebind double other. Now our tracking allocator of double used the internal rebinding mechanism of tracking allocator of int to convert the type which we are working on. It does so really not knowing what really tracking allocator of int is. It doesn't need to know that type. Like the standard vector, it doesn't know that it's using our tracking allocator. It knows it uses some allocator, and it knows that this allocator can be potentially rebound to some other type. There are rules which govern how this is done by default, so you really don't need to write your rebind mechanism, but if you really want, that's how you do it. Right there. So let's leave it for now. Okay, so we've talked about the rebind mechanism, and we know that vector internally tries to use that mechanism to create another allocator and copy it to our allocator, which means our allocator should be able to accept another allocator working on another type of objects. So what we need is a template copy constructor. Oh, sorry about that. It doesn't really need to do anything at the moment. This copy constructor takes an allocator which uses the rebind mechanism to convert it on another type. Now let's see if it compiles. It does. Well, you might wonder, that's a lot of code. But most of these functions are really optional. You really only need this, you only need this, you only need allocation and deallocation, and all other are optional. So now that we have our allocator, which we intended on tracking allocation, let's actually track them. Okay, but since we want to track all allocation done by our tracking allocator, let's just make it static. That 0 should be here. Got. There it is. And on each allocation, let's just increment the counter. And finally, let's make a way to report the total allocations. So get allocations constant. Note that I'm not using no except here, although this method would be no except. but let's leave exception safety out of this tutorial for now. Return allocations, and let's report what happened here. Get allocator, okay. Get allocations, and line, let's compile. Ah, damn it. As usual, forgot the type name, yeah. So let's see what the result is. The result is 1. Why 1? Well, remember, the allocation function takes a number of objects. So it was only called once, therefore 1 allocation. So let's adjust it slightly. Instead of incrementing by 1, let's add the object count. And now you see, we used 1 allocation to allocate 5 objects. Plain and simple. That's the basis of a tracking allocator, an allocator which tracks statistics about allocations. Now, if you're wondering how to keep separate counts on separate allocators, not a single static one, well, that's actually pretty simple, but going into details, it might be a little tricky. As you know, the allocator might be copied. So if this wasn't static, what should you copy? Previous number from the other? Go from 0? You don't know. But there's another catch. Copying or moving containers is also a bit tricky. You see, you have control over if copying containers should also copy allocators, if moving containers should also move allocators, or even if an allocator should be swapped with another allocator if 2 containers are being swapped. I really don't want to go into the details in this video because it's already quite long. You can click the link below in the description and read all the nitty-gritty details of how it works. It's a bit long, it's also optional, so you really don't need to care about these things, but if you're interested how propagating allocators really work on the inside, go ahead, you can do it. Here you have a basis of a simple tracking allocator which tracks statistics of total allocations done. You can modify it at will. Last, let's get rid of all the optional stuff and see how the most basic tracking allocator would look like. So let's remove this. Let's remove this. Note max size might be required in some standard libraries. I hope it isn't required here, but we'll see in a moment. Let's remove this one. Let's remove this one. Size type is being used all around, so let's leave it just for convenience. Void pointer and const void pointer aren't really used, so let's remove them. Pointer is being used, const pointer isn't being used, but for completeness let's keep them around. And value type is our only required element. So let's try to compile this one. Voila, everything works. So you have, I don't know, maybe 30 lines of basic tracking allocator. You can use it to track your memory. You can use custom allocators to manage memory in a better way, to use your own low-level memory libraries like Intel's thread building blocks and its scalable allocator. Really good stuff. So now you know how to really do it. It's really simple if you look at this. Let's get rid of this one. If you look at this basic version. some type defs, aliases, two methods, and a custom copy constructor. And that's it. You're done. Hope you found this informative. Hope you learned how easy it is to write a custom allocator despite all those strange details like rebinding. If you liked that video, give thumbs up, click to subscribe. If you have any comments, share them below. More code is available in the link to my homepage. See you around. Make good code.